Ready? So today we're going to look at the issue of hypothesis testing when sigma squared is unknown and needs to be estimated. And when is sigma squared unknown and needs to be estimated? All the time. So this is hypothesis testing, essentially in the real world, you might say. So we have a regression model. That's the simple regression model. And we never really estimate a simple regression model. In practice, we're always doing multiple regression, but we can work through the formulas for the simple regression model, and that keeps it nice and simple. The least squares estimator, the OLS estimator, sigma squared with a hat on top, and traditionally, we, instead of writing sigma hat squared, which would be fine, usually we write s squared. So s squared is the sum of the estimated error terms, or the residuals, divided by n minus 1. And epsilon hat is yi minus xi beta hat. So these are the regression residuals. Take the sum of the squared residuals, divide by n minus 1, and that gives us our least squares estimator of the error variance. And we use n minus 1 in the denominator in the simple regression case, but if we go to multiple regression, we have to subtract more terms in here. We have to subtract one term here for every coefficient we estimate in the regression. So if we have a multiple regression model, alpha plus beta 1 x1 I plus beta 2 x2 I plus epsilon. So we've got k equals 2 slope coefficients, and we've got the constant term alpha. So this time we're going to do s squared equals the sum of the residuals, sum of the squared residuals, divided by n minus k minus 1. So it would be n minus 3 in that case. We have 3 coefficients that we've estimated. And this term, n minus k minus 1, that's what we call the degrees of freedom. Degrees of freedom. That's a funny kind of term. It sort of sounds like you're in prison or something, and this is how big the yard is that you get to walk in. It's not quite like that. What it means is you've got a sample of size n. So you have n pieces of information, and you want to estimate this coefficient s squared. And in principle, s squared could take on any one of n values because you've got n pieces of information, but you had to use up some of those pieces of information in order to get your residuals. So given the fact that you have to use estimates of the error terms, you don't have the error terms themselves, you have to use estimates of the error terms, you have to use residuals from the regression, and in order to get those, you estimated these coefficients, and every time you estimate a coefficient, you are restricting the number of independent residual terms that you could estimate. Whether you follow that or not doesn't really matter. The point is, when you see the term degrees of freedom, it means the sample size minus the number of estimated regression coefficients. So in that case, it's n minus 3 for that regression there. And in the R output, you'll notice that they report the degrees of freedom, but they don't report the sample size unless you ask for it. But that's okay, because you could figure out the sample size if you're given the degrees of freedom, and you can look and see how many coefficients are estimated. I'm just noticing, for some reason, the color is very red today. I guess because it's fall and the leaves are changing. So my paper is turning red. And then if I have my hands here, just the reflection off my hands seems to change it. Oh well, can't do anything about that now. All right. So getting back to what we're supposed to be talking about here. Confidence intervals and hypothesis testing. So we've seen before, you have the Z statistic, and that's beta hat minus some hypothesized value, beta 0, divided by the square root of sigma squared over, and in the simple regression case, this is the formula, and we know that that's distributed n01, standard normal. But we don't know sigma squared. But we use s squared in place of sigma squared. So our Z statistic is actually going to be beta hat minus the hypothesized value beta 0 divided by s squared over the sum of xi squared. And so the change is, this is no longer standard normal. This follows the t distribution. And the t distribution is actually a family of distributions, and it changes with every sample size. It changes based on the number of degrees of freedom that you had when you estimated s squared. So we're going to put as a subscript here the degrees of freedom. Okay, so t is a family of distributions. That depends on degrees of freedom, or if you like, the sample size that you had available to you when you estimated the t statistic. So let's use an example. Suppose n equals 22. If sigma squared is known, the 95% confidence interval, that's what CI stands for, 95% confidence interval, is beta hat plus or minus 1.96 times the square root of, remember what goes in here? Sigma squared over the sum of xi squared in the simple regression case. If we use s squared instead of sigma squared, then the 95% confidence interval is beta hat plus or minus something. going to leave it blank for a moment, times the square root of s squared over the sum of xi squared. Now what goes in there? So let's just think about, we're taking account of the fact that we had to estimate the variance. So we're not as sure as we were before. So we don't know sigma squared for real. We estimate it. So we're not quite as sure as we used to be. So that confidence interval should be a little wider. Okay, uncertainty means we're going to expand the bounds of the confidence interval if we still want to encompass 95%. So the number that goes in here should be bigger than 1.96. Now, the number that we're going to use, so in the simple regression case, the degrees of freedom equals n minus 1, which in this case is 21. Okay. So what we want to do is move this up here. We want the 0.025 critical value for t with 21 degrees of freedom. Where did I get 0.025? Well, remember, it's a 95% confidence interval, so we've got 2.5% out on each tail. So we want that street address. We want the critical value that says everything from here on out is 2.5% of the distribution, and 2.5% down in this direction as well. So we want the critical value, the 0.025 critical value for the t distribution with 21 degrees of freedom. So now I have to see how to use a t-table for that. There is a t-table in your textbook at the back. So we've got standard normal in table 1, and table 2 we've got the t-table. Now, because the t-table depends on the number of degrees of freedom, what it means is for each degree of freedom, each count of degrees of freedom, you have a different t distribution. So we can't tabulate all the detail that we had with the standard normal. The standard normal doesn't change if the sample size changes. The t distribution changes. So what we get is just the areas under the curve, or we get the critical values, for the areas under the curve, but we're only going to look at 3 of them, 0.05, 0.025, and 0.005. So what we want then is that critical value for the 0.025 area under the distribution for 21 degrees of freedom. So we go down the column here to 21 degrees of freedom and read across, and that's 2.08. And so this is the table in your book. I pulled this one off the internet. It's got a little more detail in it. So it tabulates for more areas under the distribution, 0.4, 0.25, 0.1, 0.05, and so forth, down to very small tails. And as before, it gives the critical value. So if we go down to row 21, and we look for the 0.025 critical value, that's 2.08. Where are we? Just don't adjust your screen, I'll get it. There, 2.08. That's a lot of focus, isn't it? But anyway, so remember, back here I said we want a number that's a little bigger than 1.96, and we get that as 2.08. That's if our sample size is 21. Now, what if we have a smaller sample size? if we have a smaller sample size? Well, let's say we only had 10 degrees of freedom. Well, that's not a lot of data to try to estimate a confidence interval. So if we had 10 degrees of freedom, then look at that, 2.28 is the number. So that confidence interval is getting wider and wider. But suppose we had a lot of data. Suppose we had a billion observations in our data set. Well, that's almost like having the whole population. And if you had the whole population and you calculate the estimated variance, that's kind of like knowing the true variance. And if you know the true variance, then we're back to standard normal. So what would happen in that case? If the sample size is getting really large, so if you go read down the column, now you're up at 100 degrees of freedom, 120 degrees of freedom, and then, well, the next number above 120 is infinity, at least in this table, but not really. But if you had an infinitely large sample, wow, look at that, 1.96. That's what the tail, that's what the critical value would be, 1.96, which is the standard normal amount. So this is the nice thing about the t-distribution. The t-distribution, as I mentioned, it's a family of distributions that depends on the sample size. As the sample size gets infinitely large, the t-distribution converges to the standard normal. And as the sample size gets small, the t-distribution gets fatter and fatter tails. So let me see how well I can draw this. So this is standard normal, okay, and it's got these tails so that above and below the 1.96 cutoffs you get 5%. If you have a t-distribution with a very small sample size, what it gives you is a distribution sort of like this. Which means if you want to encompass 95% of that distribution, you're going to need much wider confidence intervals. But as n gets larger, then the t-distribution is starting to it's starting to take on more of the standard normal shape, and then once you get a large enough sample, then the t-distribution overlaps the standard normal very closely. In practice, once you're over a couple of hundred degrees of freedom, the t-distribution is pretty much the same as the standard normal. So it matters when you have a small sample, not so much when you have a large sample. Okay, now backing up a step, when I write the Z transform, if we use beta hat minus the hypothesized value, and we divide that by s squared over the sum of xi squared, in other words, the estimated standard error of the beta hat coefficient. Instead of calling that Z now, I'm going to call that T. All right, so this is the T statistic. And you'll see that in regression outputs. You see, they give you the slope coefficient, they give you the T statistic. So the but what they're reporting is the T statistic, if you set beta hat equals 0. So this is the one reported in a regression, in regression output. Sorry, I shouldn't scribble so quickly. In a regression output. So you'll see the typical output, which has a table would be like beta hat, and then the t statistics. Oh no, sorry, beta hat, and then the standard error of beta hat, which is the square root of the variance, and then the t statistic, and then the p-values. So that's the four things you usually get in a regression output. And the t-statistic is the z transform when we've set beta 0 equal to 0, and we're using the estimated estimate s squared, the estimated variance of the error term. So then you can think of it then, beta hat divided by the standard error of beta hat. That's the t statistic. And where that comes from is setting beta 0 equal to 0. So it's the ratio of beta hat to its own standard error. So thinking about a little example here, suppose that degrees of freedom equals 25. So n minus k minus 1 equals 25. And suppose that t equals 3.0. Okay, so we've run a regression. You get a certain regression coefficient, you get standard error, and the ratio of the coefficient to its standard error is 3.0. So then what we want to figure out is that significantly different from 0 at a 5% critical level. Just grab this this set of critical values here, these tables. So we said we had 25 degrees of freedom. All right, so that is this row. So 25 degrees of freedom, and our t statistic we said was 3. So 3 is in between that number and that number. So what that means is that the probability that we're using t values here. The probability that t is greater than or equal to 2.787 is 0.005. Probability that t is greater than or equal to 2.787 equals 0.005. And symmetrically, that means the probability that t is less than or equal to minus 2.787 is 0.005. So that means that the 99% confidence interval is bounded by 2.787 either way. All right. So probability that minus 2.787 less than or equal to t less than or equal to 2.787 equals 0.99. Where did I get 0.99? Well, we've got a 0.5% in the upper tail and a 0.5% in the lower tail. So put those two together and we've got 1% of the distribution lies outside these bounds. So that's a 99% confidence interval. And we can also do it in a hypothesis testing format, which where we choose our significance level. So if we choose a 1% significance level, then we look at the 0.5%, the 0.005 critical value, which is 0.2787, and our test score is greater than 2.787, so we would reject the null hypothesis in this case. 3.0 is greater than 2.787, therefore reject the null hypothesis. So it's exactly like what we did with z-scores. Now we're just calling them t-scores, and we have to use t-distribution critical values, which are going to be pretty close to the standard normal, but they will reflect the fact that the tails are a little bit fatter, confidence intervals are wider, critical values are higher than they would be for the standard normal. And that's all we need to do to finish up this unit. And I think on a topic like this, what you're just going to find is you just have to practice. You just have to do a few exercises, but then also you'll learn when you run a regression, you'll get used to seeing these numbers when they come out of a regression, and now you know what they mean. You know what they're telling you. So if we go into the textbook here on page 41, and I'll zoom in and refocus. Still not very focused, boy oh boy. That's what it wants to do. This is page 41, so you can pause the video, open it up yourself. But so you got the variable names, you've got the intercept term or the constant, and then the explanatory variable here. You have the coefficient value, the standard error of the coefficient, so that's the square root of the variance, the estimated variance of the coefficient. Then you got the t-statistic, so that's the ratio of the coefficient to its standard error. The t-statistic, and what they don't say, but it's the t-statistic for a null hypothesis that the true value of the coefficient equals 0. And then the p-value, that gives you that area of the distribution beyond the value of the t-statistic. So it is the smallest significance level that you could choose and still reject the null hypothesis. And then the 95% confidence interval, and it's always going to be the case if the p-value is greater than 0.05, then the 95% confidence interval encompasses 0. So you can see in this case the first 95% confidence interval goes from minus 1.53 to plus 5.91, so 0 is in the confidence interval, and so we can't rule out the slope coefficient or the coefficient being 0. But in the case of the output measure, the slope coefficient has a t-statistic of 36.36, which is way out on the tail. And you can see in the footnote here that the size of the tail is 5.4 times 10 to the minus 67. All right, so you couldn't even fit an electron in there. It's so small. And the p-value is just written 0 in that case. And the 95% confidence interval is pretty narrow. So 4.53 to 5.05. So pretty tightly bounded in that case. All right, so do you know what those terms mean? Because we're going to be seeing lots of them. And but now you understand why we use the t-distribution rather than the standard normal when we estimate the variance rather than knowing it for sure. And of course I'm not going to go through the math of why it is that we no longer use the standard normal probability density function. We use a function that looks different. It's the t-distribution. It's no longer that same Gaussian formula. But if the degrees of freedom goes off to infinity, it converges to the standard normal Gaussian density function. All right, so that's it, and we'll talk to you next time.